So I'll be discussing seismic redatuming. It's a cool application that I personally got to know about with Matteo Ravasi. He's a professor who joined KAUST last year. And we tried to apply two optimization techniques on it. Tilde low-rank matrix vector multiplication that really leverage the data sparsity of the operator. And in addition, we apply mixed precision. So two sort of approximation to reduce the memory footprint and time to solution. All right, so this is the takeaway message. In case I run out of time, at least you get the conclusion up front. So we get a huge memory footprint reduction up to 35x, starting from a dense regular matrix vector multiplication all the way through doing compression and then various reordering of the matrix to reduce not only memory footprint but also time to solution. And in addition, at the end, we get an additional memory footprint reduction by applying mixed precision. So that's the plot on the left. On the right, it's time to solution. So the lower, the better. And we're looking at 5 various hardware and looking at various incrementation for our optimization applied on the kernel. And we get up to 5x here on NVIDIA GPU. Okay, so seismic imaging, I'm not teaching anyone here, hopefully. What we're trying to do here is that we're trying to identify, using the geometry acquisition on the surface of, the Earth and moving it toward some targeted location on the subsurface of interest. Okay, so we're really trying to use some data collected at the surface and try to then target a specific, region under in the subsurface and collect or basically identify what's going on there. That technique is called or is based on the technique implemented by Marchenko, Redatuming or Redatum, which means repositioning. So that's more or less the story. So we use again the data collected at the surface and move those data closer to the surface, the region of interest, and then we can perform our imaging or inversion. This is the mathematical formulation. So there is an operator. We try to do forward and backward integration. There is this multi-dimensional convolution operator, MDC, that is involved in this operator that is known. And we're trying to get the model here. So the overall phase has a forward and adjoint. For each of those phases, there is 2 multi-MDC involved. And eventually, there is some iteration for the solver. So all in all, there is the profiling at the bottom, right? So we spend mostly 80% here, of the operation involving this operator, this MDC operator on R. Out of this 80%, when we look at the operation we actually perform on R, there is some, fast Fourier transform, some padding, and the most critical one in the middle is this batch dense matrix vector multiplication. And it's something that scales up as the size of the number of receivers and sources. So this really scale up pretty high, and this is usually done in dense format, so no compression is applied, nothing is done. We just take the matrix and do our matrix vector multiplication. So it's actually very prohibitive in terms of memory and in getting performance if we were to apply it in the original way. So just looking at the numerical example that I'll be using in this presentation, we're looking at around 10K number of receivers and sources. A subsurface model of 1.8 kilometer times 1.2 times 1 kilometer. The Redatuming grid is 650 meters. And we look at, or we focus at 8 lines of receivers, and look at the evolution of the wave across time. So this is the numerical example. On top, you see this plot showing the evolution of the wave in the y-axis. And the x-axis are those 8 lines that you see, 8 lines of receivers. So on top is the truth, okay, is the ground truth solution. And on the bottom is when we apply our Marchenko redatuming. So is delivering pretty good reconstruction error, very low reconstruction error with an SNR up around 15 dB. So the Marchenko Redatuming is our naive approach. This is when you do dense matrix vector multiplication. You don't apply any approximation, any mixed precision. This is our reference. All right, our contribution here is to basically take the kernel, batch dense matrix vector multiplication, and replace it. Replace it with a kernel that leverage the data sparsity of that operator R and do some Taylor-Rank compression and apply then the matrix vector multiplication that exploit the compressed data structure. Okay? And once we've done that, in addition, again, as I said, we eventually apply mixed precision to it. So this is our big matrix, 9K, almost 10K by 10K, given at a certain frequency slice at 30 hertz on the left. So if we select just a region of that matrix around the diagonal and try to zoom in, there are clearly some structure there that we can leverage, and where we can see some block diagonal structure, and each of those tiny matrices retain most of the information around the diagonal. As you move out from the diagonal of those blocks, if you will, the information is not that important anymore, right? It's not important toward getting the solution accuracy of your problem. So what we do is very simple. We take each of those blocks and compress. Okay, we apply an SVD-like algorithm to really retain only the most significant information from the spectrum of the matrix. So that's the matrix on the right side. So each of those tiles, if you will, or sub-matrix, is then characterized by two bases, what we call U and V bases. And now the whole idea is to perform our matrix vector multiplication by using those U and V bases. All right, so in terms of compression, there is a huge gain here just by approximating up to a certain accuracy that we know deliver an SNR very close to what the dense MVM would provide you. And just by doing the compression, we already get a 4x here in terms of reduction in memory footprint. Okay, so I'm just going to walk you through this cartoon, explaining how we do this Taylor-Rank MVM. It's not really new. I mean, this has been there. This algorithm is not new, really. Our novelty is probably in the implementation, how we implement it, and how we design it in memory so we can leverage, the bandwidth of the hardware. So this is showing a matrix 4x6 style. So we just take the matrix we get from the application, and we split it into tiles. The size of the tile, it's a parameter that gives has an impact on performance and that govern the level of concurrency. So we take each of those tiles and we do basically an SVD. Okay, we compress up to a certain accuracy, and the ranks are different. The ranks are different between the tiles, right? So that gives really a challenge in terms of load balancing, for instance. Simply because some tile may retain more information than others, basically, right? So once we've done that embarrassingly parallel phase, that initial phase that you compress, that consists in compressing all of those tiles independently, then you stack the bases. For each of those tiles, you get a U and V basis, and the whole idea here is to stack those bases together, okay? So that you can have contiguous memory access in memory. So on any architecture that you would use for for doing your operation, it will basically have a nice layout in memory, and then you can really reuse what you have already brought in the first time, and so it's sort of latency aware, if you will. So once I've done that, I pack those bases in memory, I stack them up, and then my initial dense MVM operation that you were just before calling BLAS2 level 2 BLAS kernel now gets split into various kernel calls. Okay, and the first one is basically a batch MVM. So it's a batch matrix vector multiplication with variable sizes that takes care of the V bases first. It grabs the V bases. I don't know why it's automatically changing on my behalf, but it takes the V bases and multiply them against the vector X and get you this YV structure that is transient. It's a buffer that represents this first operation. But those YV bases, we need to do some shuffling in memory and project them into the U bases in preparation for doing the last phase that consists in taking the U bases and multiply by this YU data structure. And this again gets expressed in terms of batch matrix vector multiplication. So we used to have one call to level 2 BLAS, gets transformed into 3 phases, batch MVM, and then memory shuffling, and then batch MVM, okay? All right, so how we do this, especially on GPUs, we support MPI, OpenMP on the regular x86 architecture. On GPUs, we have to do something a bit more fancy to get performance. We use streams to ensure hardware occupancy, and CUDA graph to track for us the data dependencies among various phases. Okay, so that's the first thing. We approximate, we do MVM, and I'll show result right in a second. But we can do more, actually. Okay, what we can do is reorder the matrix. The matrix, because we compress it, if we compress it with no arrangement initially, that's the 4x memory footprint that you would get. But it turns out that if you make it distance aware, right? I mean, this is usual, technique that people would do in linear algebra. If you reorder those unknowns, if you reorder them based on their distance, basically those that are strongly correlated, you put them next to each other. Those that are less correlated, you just put them far away to each other. And by doing that, you can actually improve further your memory footprint and eventually do less operation. And this translates hopefully into a faster time to solution. So we looked at two algorithms to reduce to do this distance-aware reordering, L1 and Hilbert delivered the best performance. So that is up now to 4.5 further memory reduction compared to the initial data. So 4x and now 4.5, we are around 16x reduction in terms of memory footprint, compared to the dense matrix. All right, so we do the distance reordering, matrix reordering, and then we of course look at those plots, right? Those 8 receivers. And look at the dense. This is the general way of doing our MVM. The Tyler rank, we apply only approximation without any arrangement, and then we apply L1 and Hilbert. So they all provide a good SNR. Okay, similar SNR to as if you were doing the whole matrix. So far so good. We didn't perturbate the accuracy of the problem. All right, when it comes to performance, so we get this 35x. Improvement, actually a little bit less until Hilbert. We get something like maybe 20x. And then when it comes to time to solution, we are able to improve further, the dense MVM on those 5 architecture: Intel Ice Lake, AMD Rome, EPIC Rome, Fujitsu A64FX, NEC Aurora, S6 Aurora, and the NVIDIA 880 gig. So, there is a clear improvement in time to solution as we do the reordering, on the matrix. And the last plot I show is bandwidth, because we now deal with much less data, right? We are, extracting. It's difficult for us to extract, bandwidth as opposed to when we were using the whole data, simply because we do not saturate the bandwidth. We don't have any more, since we compressed a lot, we don't have any more. Lots of data to extract bandwidth. So the idea here will be simply to run even larger problem sizes or higher resolution, for instance. So that's a clear, indication that we can do that now, right? So the last thing is mixed precision. So there is a clear improvement when you do approximation. Now we want to do, see opportunities for mixed precision. And the idea is rather simple. Those are correlations, right? So the farther you are away from the diagonal, this is where you could even, lower precision in addition to doing, algebraic compression. And that's what we do. In green, you would do FP32. This is the traditional, precision arithmetic used in this application. You could actually drop it to FP16. That's actually a key finding that we found, we looked at, a few months ago. And as you move away from that band, okay, then you can actually go even integer 8, for instance, precision. And that's what we've done here. We looked at various combination of FP32 and FP16, combination also of FP32 and integer 8, and also a last graph here on the left, FP32 plus 0. We just put FP32 around the diagonal, and just as a sanity check, we wanted to break it. And in fact, you will see that we did break it. We put 0, outside of that band, right? And when you do that, you can see that the error on the left is clearly pronounced there. There is clearly, a call for something going wrong when you actually put 0. So the data is actually not so important, but you cannot simply just remove it. You have still to keep some of it there. All right, and this is the plot showing the SNR, right? So this is the quality, right? And you can see indeed for the green curve, FP32 plus 0, it just goes down. as you, put more zeros, if you will, in those tiles. However, the other combination of precision, up to a certain bandwidth of 15 tile, they all actually are very close to your original dense MVM, as if you don't do any approximation and in addition no mixed precision. Okay? So there is a clear potential. As a preliminary performance result, we show that there is up to 20% gain in introducing, in terms of time to solution, in introducing mixed precision. So we have a kernel. We actually had to implement a kernel because there were no half precision in cuBLAS. Half GEMV, kernel doing that. So we had to implement it. It's a preliminary implementation, still delivers good performance, but we think there is still room for getting a better or higher bandwidth on the GPU. And we do this on the GPU only because, on Intel, AMD, there is no support for that. I mean, there is for A64FX, simply we didn't have time to do it. So we only showed on NVIDIA here. All right, conclusion. So this talk, you heard about Low-Rank compression, how this can really, compress big time the actual data up to 4x. Then we introduce distance-aware matrix reordering that gives the memory footprint reduction further to another 4x, factor. And then when we include mixed precision computation, we can get up to 20% performance improvement in terms of time to solution. So, the fact that we reduce data size, we really want to leverage the power of HBM technology on those hardware that I mentioned. And, it's difficult when, you deal with a problem size that you compress. So we really want to deal with a much larger numerical example. As next, we want to look at FP16, improve the performance of FP16 on GPU and also implement it on A64FX, ARM processor from Fujitsu. Explore int8 precision. We have not yet fully explored that. And as I said, investigate even larger, synthetic and field data sets. Thank you.
Thank you, Hatem. Quick question, maybe one very quick one. Did I hear that correct, that you use the built-in or semi-native reduced precision on the NVIDIA GPUs?
That's right.
Okay.
Correct.
And that is why you did it only on the GPUs?
That is correct.
Okay. Sorry, that was a personal interest question. Anyone else?
How do you decide on the low rank? What is the low rank that you choose? How do you choose that?
You mean the precision, the accuracy at which we have to compress each of those tiles? Yeah. Very good question. So we used to do it brute force, meaning we compress a certain accuracy threshold and find out at the end, our SNR, whether it looks good or not. It's not sustainable and it's not practical, this brute force approach. So we start looking at other, more mathematical oriented approach where we calculate the norm of a single tile and compare against the norm of the whole matrix. So trying to see the weight of that single tile that we're about to compress and see the ratio compared to the overall, matrix. And the ratio of those give us an indication on where to start, at least in terms of accuracy.
Sure. Let's do one.
You split the matrix into like 4x6 tiles, right?
Yep.
So maybe a silly question. Is that applicable to any matrix, or it must be a matrix with a certain very repeating pattern?
Oh, so the splitting was mostly for simplicity purposes. You can really split the matrix the way you want. The tile size really tells you how much parallelism you want to explore or expose to your runtime.
But any kind of matrix?
Any kind of matrix, yes, absolutely. So those matrices are non-symmetric, actually rectangular, so any type of matrices.
Right, thank you.
Thank you.
Okay, thanks again.